Okay, most of the student already in this VCD. Okay, we can start our class. Before that, let us recite the Kitab Al-Fatihah. Assalamualaikum warahmatullahi wabarakatuh and very good morning. Semalam slide tu boleh buka dia punya audio tu. Ada?
Boleh buka doktor, tapi itulah suara perlahan sangat. Saya dah high volume, saya dah tinggikan volume komputer pun tak boleh. Dia dengar cuma slow.
Kau pakai earphone?
Earphone pun sama. Itu pakai earphone tu doktor. Saya buka earphone pun tak dengar sangat.
Yang lain jangan. Tak dengar juga. Saya punya kat komputer okey. Yang lain pun tak dengar juga. Kawan-kawan yang lain. Nur Iman? Nabila?
Doktor sama macam Ain.
Tak dengar. Boleh dengar juga ke langsung tak dengar?
Boleh dengar tapi slow.
Okay. Right. Okay, so just a quick revision for yesterday lesson. So yesterday we have a look on the different type of the amplifier. So the classes involved is class A, class AB, and class C amplifier. And then in that lesson also you are introduced what is the amplifier distortion and the efficiency of various classes involved and power calculation of the classes amplifiers. Alright, so the amplifiers receive a signal for example, microphone and speaker is a complete set lah. From microphone it will pick up the voice, so that is the input to the amplifier. So the word amplifier is actually amplify. It will make something small to be bigger. Okay, in this case for sound, slow sound become more high and clear sound at the output. So that is the basically the the concept of the amplifier. So the transducer as a mic or other input source of the amplifier will provide a large version of signal to the output device of the amplifier stage. Alright, so there are basically covered in this lesson. So there are class A, class B, class AB, class C, and class D. Okay, so class A is the output signals. So it varies of full 360 degrees. Okay. So as you can see in figure 12.1 A, also for class A, it will full swing 360 degree from positive cycle to negative cycle. Okay. It shows that it involves the Q point of the bias at the level, so that at least half of the signal swing of the output will vary up and down without going a high enough voltage to the limited by the supply voltage. Okay, and class B in a figure 12.1b, so the class B circuit, it will provide output signal over 1/2 of the input signal cycle, which is 180 degrees. of the swing. Okay, so that is a class A and class B. Okay, as a comparison in the table, so we can see that the okay, from the table, so we can summarize that the operation of the various amplifier classes, class A, AB, class B, C, and class D. So in class B operation, normally involve the push-pull connection is obtained using either transformer coupling. So later on, we will look on the transformer coupling in the push-pull connection in class B. And so class B also using the complementary or quasi-complementary. Okay, is a combination of the NPN and PNP transistors, okay, to provide the operation and for the opposite polarity cycle. Okay, so this figure 12.2 is a example of the series fit class A amplifier. Okay, so we have the input at the base, and then we have the capacitor input, and we have the RB. So the current will flow toward the base of the transistor. So the the supply will given by the VCC. So we have the load, RC load, and the emitter will be grounded. So basically, this is the connection of the class A series fit. Okay. So the only difference between the circuit, so the class what we have discussed in the class A, which is a series fit amplifier. So this circuit have a small signal version considered to the large signal circuit in terms of the range of the volt. So the beta of the power transistor is generally less than 100. Okay, the beta value for this kind of circuit. Okay. The overall amplifier circuit using the power transistor. So this circuit is capable to handling large power of current. So that is the characteristic of this circuit. And the current, while not providing much voltage gain, yeah. So in terms of the voltage gain is lesser. Okay. So, all right. So this is the DC bias operation for the circuit 12.2 just now. So we can see that the DC bias VCC and RB is fixed. So we can calculate the IB. So IB is VCC minus 0.7 RB. Okay. So this is the IB. The IB is a flow through the resistance RB fit into the base of the transistor. So we can calculate the IB, and also the IC is beta IB, and the VCE is VCC minus ICRC. Okay, from that parameters, from the IB, IC, VCE, so we can plot the DC bias operation power amplifier. So the characteristic is as you can see in this figure 12.3. So this is a transistor characteristic showing load line and the Q point. So the Q point basically at the center. So from here, we can get the ICQ and also the VCEQ. Okay. Okay, so the value VCC, the DC load line can be drawn using the VCC and RC. As you can see that we have the value of VCC over RC on this axis, IC axis. So this is IC versus VCE. So the intersection is known as the Q point, the quiescence point. Okay. So if the DC bias collector current is set 1/2, so we can denote as a VCC over RC. So the largest collector current swing will be possible in this case. Either one, sorry. Otherwise, if the Q point is not center, so the swing of the positive and negative cycle will be unbalanced. Okay, so the Q point actually is the quiescent, which is the balance that make the input and output can have the stable swing of the waveform. Okay. All right. So the next is the AC operation. Figure 12.4. When the input AC signal apply at the figure this one. Oh, sorry. Okay, using this when we put the input signal using this circuit, so we can see the amplifier input and output varies. Okay, so figure 12.4 showing the swing of input and also the output. Okay, so different is the A when the input is lesser, but the B is much greater in terms of the input signal. So as the input signal is larger, the output will vary further around the established DC bias point until either the current ataupun voltage will reach limiting condition. Okay, for the current limiting condition is either zero current at the low end of the VC over RC, okay, at the high end of the swing. Okay. For the collector emitter voltage, the limit either 0 volt or is according to the supply voltage of VCC. Okay, so that is the in terms of the AC operation. Okay. All right, in terms of the power consideration, so there are parameters such as the P input DC, P output AC, P output AC in terms of the IC RMS, okay, and also the efficiency. So this can be obtained and calculated from the value of VCE, IC, which is we can obtain from calculation in the DC analysis. Okay, okay, and then the maximum efficiency. Okay, for the maximum efficiency, so we can calculate the maximum VCE peak to peak, which is this is equal to VCC. Okay, so maximum IC peak to peak is can be calculated using the VCC over RC in order to get the IC. peak to peak means that because of we have two cycle in one period, we have two cycle, the positive and negative. Okay, so the maximum IC peak to peak is can be calculated using the VCC and RC. Is it clear my voice? Tak ada any distortion? Tak ada.
Tak ada.
Okay.
Tak ada, doktor.
Okey je, doktor.
Okay. So the we also can calculate the maximum P output and also the maximum P input. So the P output is in terms of the AC, while the P input is in the DC. Okay. So maximum P output AC is can be calculated VCC power of 2 divided by 8 RC, while for P input DC can be calculated is VCC power of 2 is divided by 2 multiplied by RC. And then from that we can get the maximum efficiency in the percentage, which is the maximum P output AC divided by P input DC multiplied by 100% to get the percentage of the efficiency. Okay. All right. So I hope that you have tried the calculation in this exercise. Okay. So we proceed to next is the transformer couplet class A amplifier. Okay, so this is using transformer couplet for the audio power amplifier. Okay. So it is a kind of a class A amplifier, which is having maximum efficiency of 50%. If we refer to the table just now, so for class A, the power efficiency is from 25% up to 50%. So this is for class A. The advantage is the swing, it have the full swing of 360 degrees. Okay. All right. Okay, so you can see in the 12.6, so this is a simple circuit formed to the using the couplet transformer. So how the transformer action? The transformer can increase or decrease voltage or current, okay, by using the transformer. So it able to increase or decrease voltage or current level according to numbers of turn. Okay, the n one ratio to n2. So it is depend on how much the ratio ataupun turning coil for this n1 and n2. Okay, in addition, the impedance connected to one side of the transformer can be made to appear either larger or smaller. Okay, so it is whether we want to make it as a step up or step down at the other side of the transformer. So so basically for transformer there are two types. One is a step down. Step down, for example, the adapter you use for charge your handphone, so that is a kind of step down lah. Okay, the step up is from the small, we want to have the large numbers ataupun large value of the voltage ataupun current. Yeah. Alright, so okay, so the voltage transformation in this figure 12.7. Okay, so it is shown the primary and secondary. So the primary is denoted as number 1 and secondary is denoted as number 2. So for V2 over V1, the voltage at the secondary over voltage at the primary equal to the turn numbers of N2 divided by N1. Alright. While for the current, it is opposite. For I2 over I1 is equal to N1 over N2. Okay. And we have the what we call the impedance transformation denoted by the RL. Okay, so the primary side is denoted as the prime R prime L. Okay, so that is the primary primary side. Okay, so we can have the impedance transformation as RL divided by R prime L equal to R2 divided by R1. Okay, so this can be simplified by this one. Okay, R prime L equal to A the power of 2 multiplied by RL equal to N1 divided by N2 power of 2 multiplied by RL. Okay. Okay. So if we define that A is equal to the turning ratio at the primary over the secondary, where A is the turn ratio, so we can simplify like this. RL prime divided by RL equal to A power of 2. Okay. So this can be expressed for R1 and R prime L as A power of 2 multiplied by R2. So RL prime L equal to A power of 2 multiplied by RL. Okay. Okay, so this example also you can I hope that yesterday you have tried this. Okay, now we look next is the operation of amplifier stage for the DC load line. Okay, so the transformer DC winding resistance will determine the DC load line for the circuit that you can see here in 12.8. Okay, so the Y and X axis is for IC. So this is IC versus VCE. Okay, ampere with versus the voltage. Okay. All right. So the ideally the DC resistance is considered as 0 ohm, where no resistance. And as a figure in 12.8, so the 0 ohm DC load line is a straight vertical line. So this is the we consider as a AC load line. So a particle transformer winding resistance will be a few ohm, but only the ideal case will be considered in our this one. So there is no DC voltage drop across the 0 ohm DC load resistance, and the load line is drawn straight, can be drawn or draws a straight vertical from the voltage point of VCE VCEQ equal to VCC. Okay, so this we can put the straight line from here. We can get the operating point at the center. So in this case is the in IC the value is 6 milliamp. Okay, this one. So the Q-cent, so this is a Q-cent operating point. So it can be obtained as you can see at the point of the intersection of the DC load line at the base current intercept from the AC load line dengan the current of the IC here. Okay, so this is the operating point. So in class A operation, that DC bias points, it set the condition for the maximum undistorted signal swing for both collector current and collector emitter voltage. So the efficiency of the circuit, again, if you refer to table just in the previous slide, so the circuit efficiency of the circuit maximum is 50%. So the DC bias point is important to setting the operation of the class A series FET amplifier, right? Okay, next is the signal swing and output AC power. So figure 12.9, so this is the voltage and current signal swing from the circuit figure 12.6. Okay, the class A of the transformer coupled class A amplifier. Okay, so at the A is the in term of the voltage, and B is in term of the current. So VCE peak to peak can be calculated by VCE max minus VCE minimum, and IC peak to peak can be calculated. It is IC max minus IC minimum. So the output in terms of AC P output, the power output can be calculated by VC max minus VC minimum multiplied by IC max minus IC minimum divided by 8. Okay, so this is the signal swing and the output AC power. So the AC power that can be calculated using this equation is developed across the primary, because we have two sides, primary and secondary. So this P out actually is we get from the across the primary of the transformer by assuming the transformer is ideal, which is the highly efficient transformer, which is the efficiency is over 90%. Okay, so we assume it is ideal transformer. So by assume that, so we can use this equation to calculate the power output AC. Okay, so all right. For the ideal transformer, the voltage delivered to the load can be calculated using the voltage load voltage or secondary voltage at secondary equal to N 2 divided by N1 multiplied by V primary. Okay, the power across the load can be calculated by this equation, and therefore we can get the IL and also the PL. Okay, so hopefully you try this exercise yesterday. Right. Okay, next we look to the efficiency. Okay. So the input, we can calculate the input power input DC, and also the power dissipated, okay, by the transformer, can be calculated by PQ. So PQ is stand for power dissipated So this is as a heat, okay, is generate heat. Because if you realize sometime when it involves transformer winding, okay, so it will generate heat. Okay, so we need to calculate the power dissipated. So from that we can get the efficiency of the performance of the devices. Right. So try this example. All right, next is the class B amplifier operation. So for class B, as you can we have seen the table summaries for all of the classes that class B will obtain 180 swing. For that, in order to get the full swing, so we need half circuit and another combination of half circuit to get the full swing of the added load. Okay. So class B operation is provided when the DC bias leave the transistor bias in the off condition. So the transistor will turning on, and then AC is applied. And then the essential no bias, and the transistor conduct current for only one half of the signal cycle. So another part of the transistor also, when it operate opposite, so it will give another negative cycle of the waveform. Okay. So from that, we can get the input DC power. The power supplied to the load by the amplifier is drawn from the power supply that you can see in the figure 12.13. Okay, so the amount of this input power we can calculate using P input, the power input DC, equal to VCC multiplied by IDC. So the A is the block diagram, use 2 voltage supplies, while at the B using 1 voltage supply. Okay. Okay, so the current DC is the average of DC current which is drawn from the power supply. So in the class B operation, the current that we get from the single power supply can be formed using the full wave rectifier signal, whereas the when we use 2 power supply that has a form of half wave rectifier signal from each supply. So for that we can get the average current drawn from the circuit by using this one equation IDC equal to 2 divided by pi I peak. I peak mean that either positive or negative cycle. So we get the peak value of the current. And then we also can calculate the output AC power given by this equation, and also the output AC power. Okay. And the measure peak to peak output voltage can be used to get the power output AC in terms of the peak to peak output voltage. Okay. So So if we use peak to peak, we divide by 8 multiplied by RL. But if we use peak voltage peak, so it's divided by 2 RL. Okay, so this you need to make a note here. You can calculate using either peak to peak voltage output or using the peak voltage. But in terms of the division is different. One, if you use peak to peak, you multiply by 8 RL, while for peak, you just multiply by 2 RL. Okay, next is the efficiency. Okay, the efficiency that you can see the class B, the class B just now. If we back to class B. Okay, for class B, the power efficiency is 78.5%. So okay, how the table is obtained is this is how they derive. Okay, how they derive. So the percentage efficiency is equal to P output over P input multiplied by 100%. Okay, so this is a general form. In order to get any efficiency of the system, we need to divide the output, the outcome that we have, into the input. For example, let's say what the output is same to the input, so the efficiency is 100% lah. But in devices, any devices that human makes, so we cannot get 100%. Okay, in the context of COVID-19 punya vaksin pun, we can see that some of the manufacturer said that their vaccine have this kind of efficiency. Berapa percent? How much percent? This one, how much percent? So, because human create something, design something, we cannot challenge to the God, kan? Because God can create something that 100%, while we are human, we are creatures that we only can achieve 90. The highest is 99% point something. We cannot achieve 100% efficiency. So similarly, so this is a general term lah for efficiency. To either you want to calculate the voltage or current or power efficiency, but most of the time power, because in power is combination of current and voltage. So when we and also the power actually it represent how much the thing that operated. Okay, so the output divided by input multiplied by 100%. Okay, so back for the equation, this one from the previous. So if we derive this one, we can get the pi over 4 VL peak divided by VCC 100 multiplied by 100%, and then by substitute IP equal to VLP divided by RL. So in summarize that, we can say that for the class B, maximum efficiency is pi over 4 multiplied by 100%, which is 78.5%. All right. So for power dissipated by the output transistors can be calculated using this one. Okay, so just denote, make a note that Q here is for power dissipated. Okay, for power dissipated. and the dissipated power handled by each transistor. So this is for 2 transistor. This is each transistor we divide by 2. Okay, so I hope you also go through to this exercise, and then the power consideration for class B. For class B operation, the maximum output power can be calculated using this equation. Maximum power output AC equal to VCC power of 2 divided by 2RL. Okay. And maximum power input DC in terms of the DC equal to VCC maximum IDC equal to VCC multiplied by 2 VCC divided by pi RL. So this can be simplified to 2 V power of 2 VCC power of 2 divided by pi RL. Okay. So the maximum circuit efficiency for class B operation is then 78.44%. Okay. So when the input signal result less than maximum output signal swing, so the circuit efficiency is less than 78.5%. So for class B operation, maximum power dissipated by the output transistor does not occur at the maximum power input or output condition. So we can say that the maximum power dissipated by 2 output transistor it occurs when the output voltage across the load is VL peak equal to 0.636 VCC. Okay, so this equal to 2 over pi. Okay, 2 over pi. And for the maximum transistor power dissipated can be calculated by 2 VCC power of 2 divided by pi power of 2 multiplied by RL. Okay. So example, you can go through example. Okay, that is a class for yesterday. Okay, can we take a break? 5 minutes.
Okay, doktor.
Right. Alright, Assalamualaikum. Welcome back. So, tolong isi ni fill in the attendant from the link that I give before. Okay, for your test, can we make Saturday morning? Is it possible?
Saturday morning.
Possible tak?
Pukul berapa tu, Doktor?
Saya tak boleh Doktor.
Tak boleh?
Saya ada hal Sabtu pagi.
Saya kalau boleh saya nak elak Jumaat tu. Any others option tak?
Maybe Monday sebab apa? Walaupun kelas Dr. Kok tapi tak tahulah sampai pukul berapa. Nanti saya mesej Dr. Kok dulu.
Apa
Tanya
Monday?
dia.
Monday. Saya tak nak kacau Monday tu dah terlajak lah kalau Sunday ke. Tapi tak apalah kalau you all dah stick Friday tu pun saya okey je.
Baik Doktor.
Friday 3 o'clock Okay, never mind.
Okay Doktor.
Right, can you see the slide?
Yes Doktor.
Okay. Alright, so this is still in the Class B amplifier circuit. So this one using the center tap of the transformer. Before that, we have looked the ordinary transformer. So here we will look what is the advantage and disadvantage of the several type of the circuit of the Class B amplifier. Okay, as you can see in figure 12.14a, okay, so actually there are two output can be obtained here using the push-pull signal. So we can have the 360 positive and negative cycle in one side, and in another side is a negative to positive cycle. So there are two similar stage that can be used, each operating alternate cycle because of the input signal, okay? Meaning that it obtained the in terms of the polarity or the phase inversion is by using the that you can see here, the tap, a kind of transformer couple amplifier. So the opposite polarity input can be obtained using the op-amp, which have two opposite output. For example, by using a few op-amp stage in order to obtain two opposite polarity signal. So the opposite polarity operation, okay, also can be achieved by using single input and the complementary transistor. Either you can use the NPN, PNP, or maybe you can use the NMOS or PMOS. So here in figure that we can see the different way to obtain the phase inverted signal. So in figure A, so that is a center tap transformer which provide opposite phase. Opposite phase and if the transformer is exactly center tap, so there are two signals are exactly opposite. So you can see that if the tap is definitely in the center tap, so we can have two kind of different opposite phase. So this one is positive to negative, this one is negative to positive. Okay. All right, the transformer coupled. This is known as the push-pull circuit. Transformer coupled push-pull circuit. So basically, there are four sections. One is the phase splitting. So this is the input, and we can see that there are center tap here with a biasing network. Okay, and then we have the push-pull circuit connection using two different transistors. One is actually it is a kind of NPN. Both are NPN, but the emitter is sharing to the ground and also connected to the biasing networking. And then we have the push-pull output transformer, and lastly to the load, which is our speaker. Okay, so during the first half cycle of operation in this transistor Q1, so it will drive to conduction. So but Q2 is off. Q1 on, the Q2 will be off. The current I1, so it will go through the transformer, and the result, the first half cycle of the signal will be flow to the load. Okay, during the second half cycle block, Q2 will conduct and Q1 is in off state. So I2 will go through the transformer and it will result the second half cycle to the load. And then the overall signal will develop across the load in our speaker that you can see in this figure. All right, so next is the complementary symmetry circuit. Okay, so the complementary symmetry circuit is different from the previous. The previous, we use the same type of transistor, NPN, but for the complementary symmetry circuit, we use different kind of transistor, which is one is NPN and the another one is PNP. So the single input signal, okay, the single input signal apply. So C is the component at the input, the capacitor. So it will break into two part, one to the base of NPN Q1, another half will be feed into the base of Q2 PNP transistor. So the so this opposite type of transistor will conduct on the opposite half cycle of the input. In NPN Q1 transistor, it will bias into conduction by the positive half cycle of the signal. So this will give the output ataupun resulting half cycle of the signal across the load as we can see in this figure B. Okay. So the half positive cycle will be conducted. So this because at the VCC1 supply will conducted to the load, and resulting the output for that. And then during the negative half cycle of the signal PNP transistor Q2, it will conducted, and then the input, the half negative will be generated that you can see in this C. Okay. For the positive, for the first positive, the NPN only conducted, while the PNP Q2 is not conducted. So the result is half of the positive cycle, but at the negative cycle, it is opposite. The NPN Q1 will not conducted, but PNP transistor at Q2 conducted, and the output will resulting negative half cycle. So when this both positive and negative cycle combine, it will cause distortion known as the crossover distortion. So that is the disadvantage of the circuit, which is it can result crossover distortion. So crossover here, either it is, for example, you talk to your friend via your phone, through your phone, and sometimes there are a little bit gap that your voice not heard by your friend. So that kind of crossover distortion. Or maybe some of others signal cross over to your communication signal. So that also considered as the crossover distortion. So crossover distortion also can be referred that during a signal crossover from positive to negative or vice versa, okay, positive or negative to positive. So there are some non-linearity in the output signal. So non-linearity here meaning that there are loss of signal a little bit in that gap. Okay. So the result from the condition that the circuit does not give exact switching of one transistor off and other of the zero voltage condition. So both transistor may be partially off, so that the output voltage does not follow the input around the zero voltage condition. So this biasing transformer in the class AB will improve. Okay, so this is a class B, but in order to overcome this problem, so the biasing, the transistor in the class AB will improve this operation by having a bias for both transistors to be on for more than half a cycle. All right. So another type of the push-pull amplifier is the quasi complementary push-pull amplifier. So as you can see, here is using two blocks, which is the first block is a kind of two same transistor, NPN. This one is PNP. Both transistor is PNP. Okay. So in practical power amplifier circuit, normally it is use NPN transistor for both high current output device. Okay. So in the push-pull connection, it requires complementary devices, the PNP high power transistor, the PNP, because this transistor is a high power transistor, is for the purpose of the high power transistor. So a practical in obtaining a complementary operation using a same match NPN transistor for the output. Okay. So for that, okay, so 12.18. So the push-pull operation is achieved by using this complementary. So this is the Darlington pair. One is the NPN, another one is a PNP, Darlington pair. Okay, so the Darlington pair is NPN, so the PNP is the feedback pair. Okay, so this feedback pair. So the push-pull operation is achieved by using this complementary transistor Q1 and Q2. The Q1 and Q2 before the match NPN output transistor Q3 and Q4. So you can see that the transistor Q1 and Q3 form a Darlington connection. Okay, so this Q1 and Q3 is a Darlington connection, and Q2, Q4 is the feedback pair, which similarly provide a low impedance. So dia punya characteristic is it will give a low impedance drive to the load. So the resistor R2 here, okay, the R2 that can be adjusted. So this is kind of a variable resistance. In order to cross over distortion. So normally this technique is used in audio mixer. Okay, kalau you tengok dekat DJ kan, DJ dia in front of the DJ ataupun at the control room there are mixer. So that is what we call the range that you can change the range in order to overcome humming ataupun crossover distortion. So R2 can be adjusted in order to minimize crossover distortion by adjusting the DC bias condition. And the single input signal, the input signal will apply to the push-pull stage. So this will result the full cycle output to the load. Therefore, the quasi complementary push-pull amplifier is among the popular apa ni, in the group of power amplifier, right? Okay, so try these two examples. For the circuit figure 12.19, calculate the input power, output power, and power handled by each output transistor and the circuit efficiency for an input of 12 volt RMS. So this is 12.19. This one. Okay, refer to this. Okay. For the circuit, this one, calculate the input power, output power, and the power handled by each output transistor. Okay. You try example 12.10, 11, and 12. Okay. So we will come back 10:45. Okay.
Okay, doktor.
Okay. For example 12.10, hello, can you hear me? What is the efficiency for the circuit efficiency?
Efficiency, I got for 53.32%.
53.32.
Yes.
Okay, right. So your PQ?
15.8.
Okay, right, correct. So, and then example 12.11, what is the power dissipated output transistor? Anyone? Yasser? Is it Yasser? Yasser? What is your power dissipated?
I still didn't answer.
Sorry? You still calculate? So I can't hear. Yasser? What you said just now?
Yeah, I haven't answered yet.
Okay, yeah, just calculate. Any student have the answer? Already have the answer for power dissipated? Nur Hidayu? Dah ada jawapan? Zulfanizam. For example 12.11. Power dissipated. Saya kira. Can give you another around 5 to 6 minutes more. Okay, welcome back. Example 12.11. Someone, please. How much you get for the power dissipated? Najah An-Nur. Dapat tak? Nur Hidayu. Nur Hidayu Musa.
Kejap. Sekejap. 21.3 watt.
21.3 watt. And 12.12 maximum dissipated BL
0.636 darab 25 volt 15.9 volt.
Okay. Alright. Okay, so hopefully all of you can get the same answer. Okay, next we move to amplifier distortion. So the the sinusoidal signal that the pure sinusoidal signal, which is in a single frequency, so at which the voltage varies positive and negative by equal amount. Okay, so the every waveform have the polarity positive and negative cycle. Okay, so any signal varying over less than the full 360-degree cycle is considered to have distorted. Okay, so meaning that because we the full period is 360 degrees, so half of the cycle is the complete cycle 360 degrees, so the half cycle it should be 180 degrees. So if the full cycle is less more than 180 but less than 360 degrees, so meaning that it occurs distortion. So an ideal amplifier is it can amplifying the pure sinusoidal signal input in order to provide the larger output of the sinusoidal signal. Okay, so the obvious example is the microphone and the speaker. So the microphone is the transducer which pick up our voice. So our voice actually is vibration, the frequency vibration. So the vibration will be processed by the amplifier to amplify the signal. Therefore, at the output of the amplifier, which is the speaker, someone can hear more larger or more clear voice, okay, by using the amplifier. So that is the concept of amplifier. So when distortion occurs, the output will not be exact duplicate. For example, when right now you hear my voice, but when distortion occurs, so perhaps my voice become distorted. It's not clear. Maybe it is double, and because it is occurs distortion. Okay. This distortion is because the characteristic of the devices, the amplifier itself, is not linear. So in the case of non-linear of amplitude distortion occurs. Right, so this can this will happen to any classes of amplifier operation. Distortion also sometimes occur because of the circuit element and devices respond to the input signal. For example, the value of the resistance, capacitance of any passive component used in the amplifier circuit itself have problem in terms of the functioning of that component. So there are one technique for describing distorted in the period of waveform by using the Fourier analysis. Okay, so the Fourier analysis, in other words, can be used. It is a technique to describe distortion. Okay. So a method that describes any periodic waveform in terms of the fundamental frequency component and the frequency component at integral multiples. Okay. So these components are called the harmonic component or harmonics. For example, signal that originally 1 kilohertz could result after this distortion in the frequency component at 1 kilohertz, and harmonic components at 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on. So the original frequency of 1 kilohertz is called the fundamental frequency. So those at integer multiples are the harmonic. So for example, 2 kilohertz component is called the second harmonic, and so on. The 3 kilohertz is third harmonic, and so on. Okay? So the fundamental frequency is not considered a harmonic. So the fundamental is the first 1 kilohertz. So that is the fundamental, the harmonics. So the Fourier analysis does not allow for fractional harmonic frequencies, only integer multiples of the fundamental. So the the harmonic distortion can be calculated in term of the percentage. So nth harmonic is referred to the numbers of kilohertz. As I mentioned just now, the first 1 kilohertz is the fundamental. The another 1 kilohertz, which is the second kilohertz, third kilohertz is considered second and third harmonic. Fourth 4 kilohertz is fourth harmonic, and so on. So nth harmonic distortion is numbers of the harmonic. Okay. The signal is considered to have the harmonic distortion when there are harmonic frequencies component, not just the fundamental component, because we are not considering the fundamental, the first 1 kilohertz. If the fundamental frequency has the amplitude of A1, the nth frequency component has the amplitude of A_nth. For example, we have 4 harmonic. So we get the amplitude of A4 divided by the fundamental A1 multiplied by 100% to get the percentage of harmonic distortion. So the fundamental component is normally larger than any harmonic component. Okay. For example, this 12.13, calculate the harmonic distortion component for the output signal having fundamental amplitude of 2.5 volt. So 2.5 volts is the fundamental. The second harmonic is 0.25 volt. The third harmonic is 0.1 volt. And fourth harmonic is 0.05 So we have basically we have 3% the harmonic distortion that need to be calculated. Right, try that one. So how much percentage for the second harmonic distortion, D2?
D2 10%,
10%, D3, and D4?
D3 4%, D4 2%.
Alright, okay, thank you. Alright, so next we look the total harmonic distortion. So when the output signal has a number of individual harmonic distortion components, so the signal can be seen as a total harmonic distortion. So it can be calculated by percentage of total harmonic distortion given by the square root of d to power of d2 power of 2 plus d3 power of 2 plus d4 power of 2 plus etc multiplied by 100%. All right, based on the example 12.13, calculate the total harmonic distortion for the amplitude component. Okay, so we have until 4 just now. So actually there are 3 components that need to be summing to be total up. So how much you get the percentage of THD? Okay. Berapa dapat percentage THD? Anyone?
10.95.
Yeah, 10.95%. Okay. Right, thank you. Okay, next is about the spectrum analyzer. So one of the equipment that you can use to see the harmonic of the signal is by using the spectrum analyzer. Okay, so it will allow the measurement of the harmonic. So if you I believe during your degree you have looked and try in lab the spectrum analyzer, where in the spectrum analyzer you can total up, okay, you can summing up all the spectrum, the harmonic spectrum frequency spectrum that obtained in the spectral analyzer. So this equipment, spectral analyzer, it allow you to measure the harmonic present in the signal by providing the display of the fundamental component of the signal and numbers of harmonic involved. Okay, so by using this analyzer, you can it can be allowed to see precise measurement of the harmonic component of the distorted signal by filtering out each of these component and giving a reading of all of these components. Okay, so as you can see in 1220, so this is we talk about the second harmonic distortion waveform for the obtaining a second harmonic distortion. So because the first harmonic is considered as the fundamental, okay, the fundamental. So we know that one cycle is the full cycle of period is in 2 pi, 2 pi in the scale of omega t. So in this figure, you showed it shows to you that the waveform using to obtaining the second harmonic distortion. So a collector current waveform, as you can see, based on the IC, IC. So in the peak to peak, we have the IC max and also the IC min, and the center is the ICQ, the quiescent of the IC. Okay. So for that, the IC can be or it is approximately to ICQ plus I0 plus I1 cos omega t plus I2 cos omega t. So the current waveform, it contains the quiescent current denoted by ICQ, so which occurs with zero input signal, and in additional DC current. DC current is the denoted as a IO. It is the non-zero average of the distorted signal. The fundamental component of the distorted AC signal is denoted by I1, and the second harmonic component I2 at twice the fundamental frequency. Okay, so the other harmonic are also involved in this equation. Okay, this one, this equation IC approximately to ICQ plus I0 plus I1 cos omega t plus I2 cos omega t. Okay, from that we can okay, we can determine the second harmonic distortion, which can be expressed, okay, as follows. Okay, D2 equal to the magnitude of half VCE max plus VCE min minus VCEQ divided by VCE max minus VCE min. Okay, so the magnitude of that multiplied by 100%. Okay. So example 12.15, calculate the second harmonic distortion if an output waveform display on the oscilloscope provide the following measurements. So you can use the equation 12.34. It's straight away giving you all the component VCE minimum, VCE max, and also VCEQ. just put into the equation and straight away you can get the you can calculate the second harmonic distortion. So based on the solution that you will get for A is 2.38% distortion, while for B it will give 0%. So meaning that there are no distortion. Okay, so next we look on the power of signal having distortion. So when distortion happen, so the output, okay, of the power can be calculated for the undistorted signal. Will face a problem on that. So when distortion is present, the output power delivered to the load resistor RC due to the fundamental component of the distorted signal can be derived as P1 equal to I1 power of 2 multiplied by RC divided by 2. And then we can get the total power. Okay? The total power due to all the harmonic component can be calculated as follows. Okay, so ni RC over 2 macam tak clear this one. RC over 2. P equal to I1 squared plus I2 power of 2 plus I3 power of 3 power of 2 plus etc multiplied by RC divided by 2. Okay, and then for that we can summing up all the total power can be expressed in the total harmonic distortion by P equal to 1 plus D2 power of 2 plus D3 power of 2 plus etc multiplied by I1 power of 2 multiplied by RC divided by 2. So this equal to 1 plus THD power of 2 multiplied by P1. Okay, try the example 12.16. Okay, berapa yang dapat ni? P?
P1 64
64 watt.
64 watt.
And then power, total power?
Total power 65.08.
Okay. So my calculation is 64.64 watt.
Oh.
Okay, almost 65 lah. Okay. Okay, thank you.
Is it the THD equal to 0.13, Doctor?
THD here I just 0.1.
Oh, okay. Thank you, Doctor.
Okay, next is the the graphical description of the harmonic component. So this is to give you illustration what is the harmonics is look like in the spectrum analyzer, and I believe that you have looked this before using the spectrum analyzer. So I think in oscilloscope also can be seen this combination of multiple signal. Okay, so distorted the distorted waveform which occurs in a class B operation can be represented using Fourier analysis as the fundamental by using the harmonic component. So as we can see in figure 12.21a, okay, this one. So it shows a positive half cycle such as the type that it will result in one side of the class B amplifier. Okay, so we can see that half of the cycle is generated at the output. Okay, and then another half cycle is zero. Okay, so by using Fourier analysis technique, we can obtain the fundamental component of the distorted signal, as you can see in this figure. Okay, B 12.21b. So the second and third harmonic component can be obtained as you can see in C in here. And also D is a third harmonic component. And then by using the Fourier technique, we can construct the distorted waveform by summing or adding all the fundamental and harmonic component. Okay, so you can see in the E. So in E, all the first, the fundamental, the second, and the third harmonic is overlap, is summing up. Okay, in general, the periodic distorted waveform can be represented by adding the fundamental component and all the harmonic component. So this will varying amplitude and at the various phase angle. Okay, so you can see that the blue one is the waveform due to the fundamental. Okay, the fundamental one, and the second below it is the second and the third harmonic. Okay, V1, and then we have a V2, and lastly the small one is the V3. Okay, from that, the summing we can see at the second cycle, we can see the distorted of the harmonic due to the combination of the harmonic. Alright, next is the power transistor heat sink. Okay, heat sinking. So one of the reason that we use the heat sink is to make the heat transfer become because sometimes our component, okay, the amplifier is generate heat, so we need that we use the heat sink is to take out the inside heat and to give the device a good ventilation, for example. Okay, so the integrated circuit are used for a small signal and the low power amplification, and most of the high power the application of the high power application, it require power transistor. Okay, so this power transistor is one of the component which generate heat, the power. So this heat will related to the power losses. Yeah, power losses. So improvement in production technique is have provide higher power rating in a small size packaging cases. Okay. So these have increased the maximum transistor breakdown voltage and have provide faster switching power transistor. So the maximum power handled by the particular device and the temperature of the transistor junction are related, since the power dissipated by the device cause an increase in temperature at the junction of the device. So obviously 100 watt transistor will provide more power capable than 10 watt transistor. On the other hand, a proper heat sinking technique will allow operation of the device at about 1/2 its maximum power rating. Of the two types of bipolar transistor, there are generally two types, which is the germanium and silicon. So for silicon, the typical maximum junction temperature can be generated is from 150 to 200 degrees Celsius. Okay, so it can sustain until that temperature. While for germanium is lower than that, 100 to 110 degrees Celsius. So for many application, the average power dissipated can be calculated using this equation, PD equal to VCE and IC. So this power dissipation, it will allow only up to maximum temperature. Above this temperature, okay, if above this temperature, the device power dissipation capacity become reduced. So at the higher case temperature, the power handling capacity is reduced down to 0 watt at the device maximum case temperature. Okay, so that's why it's very important to know, to calculate the power dissipated in order to make sure our design can give the optimum power requirement. Because some certain device, when we want to use the amplifier, we need a certain specification. What is the optimum power that we need? So if we fail to calculate the average power dissipated, sometimes when it happen, the power losses due to temperature rise, so the optimum power cannot be achieved. Okay, so this will affect to the performance of device that use the power amp. Okay, so this is a example, the heatsink. The heatsink, you also can see it when you open the CPU, computer CPU. You can see on the top of the processor, the CPU processor. So there are a metal, look like more. I think the size is more bigger than this, attached to the top of the processor, the IC processor. So this is actually is to bring all the temperature generated by the ICs of the component to outside, to bring the internal temperature outside from the devices. So for do that, it will allow the performance become improved. So that is the purpose, or the reason, the objective is using the heat sink, power heat sink. All right. So when we use the heat sink, so it will produce the transistor dissipating power has a larger area from which it will transfer the heat into the air. Okay, so sometimes in CPU we have the fan, blower fan. So if you notice in our laptop also have the apa tu, kita punya power exhaust fan. So this exhaust fan will bring the heat which is transfer from the heat sink outside from our laptop ataupun computer. So for that, it will increase the performance of our devices. Okay. So sometimes even with the infinite heat sink, either we do not use the heat sink for which the case temperature is held at the ambient air temperature. The junction will be heated above the case temperature and maximum power rating should be considered. Okay, so in the figure 12.33, so this is the typical power derating curve for a silicon transistor. So we can see that in terms of the watt, okay, so when if the temperature rise up to 80%, I think around 75 or above that, so this 100 degrees Celsius to 200 degrees Celsius, so we can see that the performance, okay, the maximum total device dissipation become decrease. Yes. So this is that's why the temperature control is very important in all of devices. And if you have experience to enter to the server room, so you will notice that server room is very cool area, because they want to sustain the temperature The server, because the server, the computer itself, the CPU, it generate heat. So that's why at the server room, they provide the air conditioning with a lower temperature to maintain the power of the power and the temperature generated by the component, normally in power amplifier. Okay, so in terms of the mathematical, we can calculate the device. We can calculate the power derating temperature by PD temp 0 and PD temp 1. So it is a maximum power dissipation at the temperature specified, and the derating factor is the value given by manufacturer in the unit of watt or milliwatt per degree temperature. For example, this exercise below is given that derated temperature. So this is normally will be given by manufacturer who produce the IC ataupun the transistor itself. So if derating is required above 25 degrees Celsius by derating factors of 0.5 watt per degree Celsius at the cases temperature of 125 degrees Celsius. So find the maximum dissipation, okay, for 80 watt silicon transistor. Right, how much we get? The PD, the maximum power dissipation.
Doktor, 55.
55, not correct. This is a PD, calculate the PD for 125 degrees Celsius. So you have the PD 25 degrees Celsius minus 125 degrees Celsius minus 25 degrees Celsius multiplied by 0.5 watt per degree Celsius. So the PD 20 degrees Celsius is given 80 watt minus 125 minus 25, we get 100 degrees Celsius multiplied by 0.5 watt. Apa yang dapat?
Uh, 30.
30 watt. Okay, right. Okay. All right. So this is the the thermal to electricity analogy. Okay. So from this is in subject apa ni? Dia dalam this is how we convert from thermal to in term of the electrical analogy. So from that electrical analogy we can calculate in term of the mathematically. Okay. So the thermal analogy of the power transistor. So as you can see in figure 12.24. Okay, so when we apply the power, actually okay, on the top here is the junction temperature. Okay, the below it is the transistor, and then we have the case temperature, the isolator, heatsink, okay, heatsink temperature, and also the heatsink. So the below is the heatsink, and then we have the ambient temperature, denoted as a TA. So each of the the component is represented by the mathematical representative. Junction temperature is Tj, and Tc is the case temperature. The TA is the ambient air temperature. So it's related by the device heat handling capacity temperature. So at the right side from this figure, that is the representative as electrical analogy. So we can represent it as the total thermal resistance, transistor thermal resistance, insulator thermal resistance, and heatsink thermal resistance. Okay, for that we can using electrical analogy to derive the in terms of the mathematical, in order to get the value of thermal, how to calculate the thermal. It's not only just to get the temperature overall, but we can break it into each of the component. In this case, we break it into the junction temperature, transistor, the case, the insulator, the heat sink itself. So all of this can be represented as a mathematical symbol in order to calculate, to find out the heat transfer. All right, and then we also can use and apply the Kirchhoff law based on the circuit here, this one. From this circuit, we can use a Kirchhoff voltage law in order to calculate the temperature. So the Tj, the junction temperature, equal to PD, the total thermal resistance plus the ambient temperature. Okay, the ambient temperature. All right. Okay, so okay, try this to calculate this one. Example: a silicon power transistor is operated with the heatsink. The heatsink of thermal resistance. Okay, the heatsink of thermal resistance the transistor rate 150 watt has the transistor thermoresistant junction to case, and the mounting insulation has the insulated thermoresistant case to heat sink. So what the maximum power can be dissipated if the ambient temperature is 40 degrees Celsius and the TJ max, okay, the junction temperature maximum is 200 degrees Celsius. So in order to calculate the PD, so PD can be calculated using this this formula. PD equal to TJ minus TA divided by the transistor thermoresistant plus the insulated thermoresistant plus the heat sink thermoresistant. Okay, this one. So what the value of PD? What maximum power? The power dissipated. Nurul Alia, have you got the answer?
Doctor, the value of TA is 40, right?
TA, yes, 40.
Okay, thank you.
Ambient.
Uh, 61.5 watt.
Okay, correct. 61.5 watt. Thank you. All right. Okay. All right. So the last one is Class C. So it is not much we will discuss on the Class C. Even though Class A, Class AB, and Class B are most used as a power amplifier, Class D amplifier are popular because of it's very efficient. But Class C amplifier not used as an audio amplifier, but sometimes it will use as a tune circuit in a communication. Okay, so this is a class C. Yeah? In figure 12.25, so this is a class C amplifier circuit. So a class C amplifier circuit, it is biased to operate for less than 180 degrees, 180 degree of the input signal cycle. So the tune circuit in the output, however, will provide a full cycle of output signal for the fundamental or resonant. Sorry. So you can see that the inductor here is act like the resonant frequency of the tune circuit L and C, tank circuit. L and C is known as the tank circuit. The type of the operation is therefore limited to use at one fixed frequency as occurs in the communication circuit. For example, in communication circuit, they will fix the frequency. The operation of the class C circuit is normally not popular used in the large signal of power amplifier, but most of the time it will use as a tune in a tune circuit in communication. So for the class D amplifier, a class D amplifier is designed that it can operate with digital pulse type of signal, because the class D, it will give in terms of the pulse, and efficiency is over 90% is achieved using the class D amplifier. So this is quite desirable power amplifier. Okay, it but however, it will convert any input signal into the pulse type of waveform. So as you can see in figure 12.26, so this how the sinusoidal signal, it converted into a pulse type of signal using some form of the sawtooth or the chopping waveform to be applied with the input into the comparator type of the operational amplifier circuit. So it will representative the pulse type signal that can be produced. Okay. So the combination of the input waveform, as you can see in the blue color, okay, the waveform, plus the sawtooth chopping waveform. So this combination will generate the digital waveform as illustrated in this below figure. Okay. So all right, so the 12.27, the figure 12.27 shows the block diagram of class D amplifier. So it consists of the sawtooth generators, this one, from the sawtooth generators, and then the comparators, amplifier, low pass filters, and the feedback. Okay. So this is the block diagram of that. So the in this block diagram, what you can see is the unit need to amplify the class D signal, and it will convert back into the sinusoidal type signal by using low pass filter here. So this low pass filter will be used to convert digital back to the sinusoidal. So since the amplifier transistor device used to provide the output either in the state on or in the state off, so it can provide current only when they are turned on. So by the little power loss due to the low on state of the voltage, okay, since most of the power applied using this amplifier, it will transfer to the load. Thus, the efficiency of the circuit is typically very high. Okay? So the power MOSFET device have been widely been used as the driver device for the Class D amplifier. Right. So that is the Class D. So for Class C and Class D is not much we discuss on, because the most popular is Class A, AB, and Class B. Okay. But Class C and Class D is not much popular. But therefore we not discuss detail on that. But in certain area, it's still being used. For example, Class D in terms of the efficiency is high, up to 90%. Okay, punya performance. While the C amplifier Class C is normally used as a tune circuit for communication. Right. So okay, so the important conclusion that we can discuss for yesterday class and today is amplifier. Okay, we have looked the Class A amplifier. Okay, so the Class A, again, the Class A amplifier, the output can be conducted in the full cycle, okay, 360 degrees, full waveform cycle. While for the Class B, it can conduct 180 degrees. So meaning that if we want the full cycle, we need to have the half cycle circuit generator combined with another half cycle circuit of generator in order to get the to provide the full cycle. And the Class AB, the output stage, it can conduct between 180 degrees up to 360 degrees. 360 degrees. Okay, so it can provide a full cycle at less efficiency. Okay? And Class C and Class D. So Class C, the output stage conducted apa ni, Class C output stage conduct for less than 180 degrees, while Class D has operation used as a digital or pulse signal. Okay. Okay. So in term of the efficiency, Class A and Class B, Class A maximum efficiency just 25%. So this without using the transformer. While by help using the transformer, it can extend it up to 50% in terms of the efficiency. That is for Class A. While for the Class B maximum efficiency, it can rise up to 78.5%. So in terms of the power consideration, so we have discussed about the input power and the output power and also the power dissipated. So each of the classes of the amplifier have these three elements related to the power. Okay, input power, output power, and also the power dissipated. And for the efficiency, we will divide the output power divide by the input power in order to get the efficiency. Okay. And then we look the push-pull complementary, the operation circuit, and then we have discussed on the harmonic distortion and also the heatsink. All right, I think I have covered on this in this topic. So please give emphasize on this topic because this will be asked in your test. Okay, this is tips lah for you. Please
Apa dia doktor?
please emphasize to study
Emphasize.
back in this amplifier ni lah, classes amplifier. Okay, because I will ask about this on your test. Okay.
Satu soalan. Is it only
Okay.
one question, doctor? Or there are several questions?
At least 2 questions.
At least 2 questions. Okay, thank you, doctor.
Okay. So any questions so far? Anyone? Tolong isi tu attendance, fill in your attendance for today. So I think if you don't have any question, or later on if you want to ask me, you can WhatsApp or call me. Okay. I think that's all for today. Thank you for giving attention to my class. Hopefully I can I can deliver my knowledge in this session. Hopefully you can understand all the lesson delivered to you. Right, thank you.
Thank you, doctor.
Thank you, doctor. Thank you so much.
Bye-bye.
Thank you, doctor.
Thank you, Doctor.
Oh, doktor,
Alright,
tomorrow class ada tak ada?
Ada. Pagi.
Ada, pagi.
Itu yang saya nak discuss tu, kalau kamu nak buat test hari lain, sebab kalau pagi buat kelas, lepas tu tak ada masa kan untuk study.
Boleh,
pulang
insyaAllah.
lah.
Boleh, insyaAllah.
Boleh jawab. Okay.
Terima kasih.